Specific speed is the unitless or dimensionless parameter that we can use to calculate out which style of pump is the most efficient to use. So specific speed we're going to define as NS. We're going to use a prime for this first one. I'll explain it in a second. So the specific speed is derived from the coefficient of flow versus the coefficient of head. Specifically, we've got CQ star to the 1/2. So that is CQ to the 1/2. The star just means that we're evaluating the coefficient of flow at the best efficiency point. And then we're going to divide that by the coefficient of head star. Once again, our coefficient of head at the best efficiency point, raised to the 3/4 power. And so if we actually write those coefficients out and cancel out the units, what we're left with is NQ star to the 1/2 over GH star to the 3/4. So as I look at this, I can calculate this out. Now this has to be done in a dimensionless manner. So we're talking head and feet. Q would need to be in cubic feet per second, N would be in rads per second. Now typically, as you're thinking back to those pump curves that we looked at, Q is not in cubic feet per second. Head is in feet, but impeller speed isn't given to us in rads per second. On our pump curves and everything, they're going to say GPM. They're going to say RPM. So there is what the book refers to as a lazy specific speed, but it is a much more common specific speed. Now, this is one of the times where I harp on units through the entire course. Units are going to be important here, but then again, not. And what I'm saying is we're going to put together another specific speed, and we're just going to call it NS without the prime. This is our non-scientific one. We need to make sure that we use the right units when we input them into the formula, but we're going to consider the entire thing a dimensionless parameter. So what I'm saying is, so instead of using N in rads per second, we're going to have N in RPM. So we're just going to look and see what is our RPM. And then we're going to take our flow rate in gallons per minute, raise that to the 1/2, and then we're going to divide that entire thing by our head in feet and raise that to the 3/4. So just completely ignoring the gravity. And so this is a much quicker number to calculate out because you can look right on a pump curve or right from your equation and go, okay, RPM is this, GPM is this, head is this, done. And so there is a conversion factor between the two. If you actually crunch out all of the constants, you'll find that to convert from NS to NS prime, it's 17,182 N prime S. So NS is a much larger number than NS prime. So, and why this is important is that the specific speed directly relates to what the most efficient pump to use is. So a low NS means that you have a low flow rate and a very high head associated with it. That's what's going to be the most efficient. A very high NS is going to mean that you're going to have a low amount of head but a very high flow rate. And so this equation is important, so let's box it. You'll be using this one a bit. So let's take a look at a chart that just shows us so we can look at the amount of efficiency per NS. So up here along the left, this gives us our efficiency in percent. Along the bottom here, we just have our straight NS from 500 to 15,000. And you can see between 500 and 4,000, so we have an NS 500 and 4,000, the centrifugal pump's the best. Especially as you get in that upper end, if you're in the 3,500 range, does that mean you can't use a mixed flow? No. It's not until you hit 4,000 that the other pump becomes more efficient. You could use it, it'll just be less efficient. And so that mixed flow runs between 4,000 and about 10,000 for for the axial flow. Once again, we can see, so at 9,900, can I not use an axial flow pump? No, it's just that the mix flow will be more efficient. And then when we're at anything bigger than 10,000, we'll use an axial flow pump. And so this is a quick way to calculate out what kind of pump we're going to use. Now, it also drives vein shape. I'm going to pop this up here, and I knew I was going to be writing over that. I'll just leave that up there. These are just a couple different pictures. This one's from your book, just showing how the impeller shape and design changes depending on the specific speed. And this one here is one I got from someplace else. I don't remember if this is out of the engineering handbook or if it's out of Mark's standard handbook for mechanical engineering. But once again, just showing how the vanes and everything work out on specific speed.